Hey guys, this is John. So this week we started studying the simple harmonic oscillator, in particular the mass spring system and the pendulum system. And these were the equations that we used to calculate the period. The videos did a great job in telling you how to use them, what these parameters all mean, and how to manipulate either your K, your M, or your L to achieve your optimal period that you want. What they didn't tell you is where do these equations come from? And it's like, come on, we're doing college physics. We can do better. So this video is going to discuss how this weird 2 pi times square root of m over k thing came about. So here's my claim. This is how we build t. T equals to some constant times 1 over omega, with omega represented by omega squared equals to negative a over x. Okay, it's just as confusing and obscure as why those videos just throw out these equations for you, but bear with me at least through this example. So for the mass spring system, we started with Newton's second law. Hopefully it's very easy by now. F equals to ma. M times a equals to negative kx. This is Hooke's law. And we're going to negative a over x, which we move the x to the left, we move the m to the right, move the negative sign to the left. We are left with k over m, or omega squared. And so omega equals to the square root of the thing, square root of k over m, and our t equals to some constant times 1 over omega, which is some constant times square root of m over k. We're pretty close, right? We got the square root of m over k ready, and the constant can be easily tell that it's just 2 pi. So this works, and we figured out the constant being 2 pi. Now we're going to talk about why is it? What's the reasoning behind this short little process? Well, the science turns out lies in the units. So if we write down the units for the period, it's going to be seconds. If we write down the units for acceleration, this is meters per second square. And I don't know if this gives you enough hint, but you see that we take the square root, probably because we want to get from meters per second square to second by taking the square root of the unit. And that's totally correct. In fact, we divide the acceleration by x, and we divide the acceleration by x to get rid of the meters on top of it. So if we keep the step flowing, get negative a over x with a unit of 1 over second square, and this is omega squared. Omega, which is the square root of the thing on top, has a unit of 1 over s, and 1 over omega gives us units of seconds, which is exactly what we want in terms of units for the period. So hooray, right? Except for the 2 pi. Why do we need a constant of 2 pi? to make everything work. Well, it turns out that's the difference between how nature and human count things. So nature and human. We human like integers. Well, I'm going to say we love integers. It's easy. We can represent it with our fingers. Everything is great about it. What's not to love? Love integer. And so when we count cycles, well, cycles is closely related to periods, of course. We said 1 cycle, 2 cycle, and 3 cycles. Our nature, on the other hand, which they predate the first existing human beings by a couple billion years, they really like angles. And in particular, radians. If you're not familiar with radians, just remember that 1 cycle equals to 2 pi radians. Well, this explains a lot by now. So instead of 1 cycle, nature says 1 2 pi, 2 2 pi, and 3 2 pi. And so by comparing the rate of nature count and the rate that human counts, we're seeing that nature counts 2 pi times faster than us. And with this process here being totally natural, natural, quote unquote, it's going to be 2 pi times faster than the speed of our human counting when we're converting it back. And so instead of having t equals to simply 1 over omega, we're going to slow omega down by dividing it with 2 pi, giving us t, well, this is the wrong one, t equals to omega divided by 2 pi. This is the conversion factor between cycle and radians, giving us 2 pi times 1 over omega. And that's exactly what we have here. Well, that's a bad looking pi, so I redraw that. So that's how we get it. I'm going to do another example using the angular system. So everything here is linear. We're having x, we're having a, we're having v. In here, we're going to dealing with theta, omega, and alpha. So let's convert it. T is still 2 pi times 1 over omega. This stays the same. Omega squared, instead of negative a, we're having negative alpha, because this is the acceleration. Well, linear acceleration. This is the angular acceleration. This is the linear distance. And for the angular distance is simply the angle, theta, represented on here. So still Newton's second law. F equals to ma has become tau equals to I alpha, with tau being the torque, I being the moment of inertia, and alpha being the angular acceleration. So I alpha, well, I should have a negative sign here. Oh, no, we have this negative sign later. This equals to, now we have the negative sign. Negative tau is F cross R, so it's mg. Well, I'm going to write F cross R being negative mg times L times sine theta to compensate for the cross product. And at a small angle, we approximate it as negative mg L theta. Well, if you graph sines and cosines, all right, this is our sine. This is sine theta, and this is our theta. When angles are really small, sine theta is basically, well, they are very close, so we approximate that. And we're finding negative alpha over theta. So before that, we're going to convert I into, so this is the moment of inertia of a mass L distance away from the center, giving us the moment of inertia of ml squared times alpha equals to negative mg L theta. Clean things up a little bit. We move the L to the right, we move the theta and the negative sign to the left, leaving us with, this can get away now. Leaving us with negative alpha over theta being g times L over L squared equals to g over L equals to omega squared. That's a bad looking square. So omega equals to square root of g over L, and our t equals to, let's say, 1 over omega divided by 2 pi. This is 2 pi divided by omega equals to 2 pi L over g, which is exactly the equation given in the video. So it turns out this is an interesting case. I'm going to write homework here. For a pendulum, we can describe it using the angular system listed here, or they also have a distance for us. And so we can also use the linear system to figure the same equation out. So if you're interested, here's the homework for you. Derive t equals to 2 pi square root of L over g using the linear system, and hopefully you will recover the same equation. Yeah, that's the end of the video. Let me know if you get the homework, if you successfully calculate it, or if you run into problems. You can always shoot me an email for that. See you then.